In the previous slide, we saw that there was a method, getIndexed, that I kind of glossed over. This method took a string as an input and returned an integer representing what array index the value should be stored at within the hash table. The big question then is, what did this method do? And the answer is that it hashed the string. Hashing is a process that derives a fixed size result from an arbitrary input. And what I mean by that is that any string of any length, when hashed, would return a fixed size, or in this case a 32-bit integer, hash value. Fixed size simply means that every input returns a hash code of the same size or type. The hash codes we'll be looking at are 32-bit integer values. But some hashing algorithms return smaller values, and some return much larger values. For example, there are hashing algorithms that can return hash codes that are thousands of bits long. But for the sake of time and simplicity, we'll be looking at hashing algorithms that return integers. Now, hashing algorithms have several properties. One is an invariant, and some are ideals. The first is stability. And a stable algorithm returns the same output given the same input always. So if you pass in the same string a million times, you should get that same hash code value back a million times. It's an invariant. Every hashing algorithm has to be stable. If it's not stable, it's not useful. Uniformity is another thing that we really look for in hashing algorithms. Now, a uniform hash is a hash that is distributed evenly throughout the available range. So if we're talking about 32-bit integers, that's really 4 billion values, give or take, that we're working with. So if you pass in a million strings, you'd expect to see, roughly a million values. Now, there are some mathematical rules that basically say, hey, look, you're gonna have collisions. You're not gonna have perfect uniformity. And it's impossible to have perfect uniformity because there's certainly more than 4 billion potential strings in the universe. So once you've given, more strings than there are potential integer values, you're going to have some inputs that produce the same outputs. Efficiency is another important feature of a hashing algorithm. If the hashing algorithm isn't efficient either in time or in space, those are things you might not want to use if you're talking about something that needs to be done billions of times in a process. If it takes 3 milliseconds to do something and you need to do it 3 billion times, that's a long time. If you can cut that down to 3 microseconds, you've saved multiple orders of magnitude off your processing time, and that's something that you need to look at when you're hashing. Finally, we have security. For some problem domains, security is second only to stability. And what a secure hash says is that given a hash value, finding an input that could derive to that same value is infeasible. So if I hash a string and I get a result back, I don't want to be able to give that hash code to someone and have them be able to figure out another string or perhaps the original string that led to that hash value. We won't be talking a lot about secure hashing in this module, but I just wanted to raise it as an issue. The hash algorithms we're going to look at aren't secure, and there are secure algorithms available. So if you're looking at a problem space where your hash value is being used for something that requires security, please make sure you're researching the hash algorithm you choose carefully.